Okay. All right. If you have any questions, excuse me, about the test or your grades, then see me individually. Just as on the test, I know some of you got a little bit slammed on the very first page on the true-false. Just make sure that you understand if you mark something as true and it's false or vice versa, just make sure you understand why it is the case. Okay. And also then that take-home quiz, you can turn that in either Wednesday or Friday of this week, whenever it is. Okay, but have that in to me by the end of the week. All right, so we're starting a new unit, and this new chapter 15, and so we have 2 chapters to go, 15 and 16. All right, with 15 is all about integration. This time we're integrating functions of more than one variable, and we're going to be integrating them initially over just plain old rectangles, and then we'll go from there to other more general regions that we'll be integrating them over. And then we'll be going on to using different coordinate systems to assist us with integrating some functions, the spherical coordinates, polar coordinates, and cylindrical coordinates. So 3 different coordinate systems that can help us integrate over certain areas. So anyway, the first section, 15.1, introduces us to what it means to have an integral over a rectangle. So there's going to 15.1, double integrals over rectangles. All right, so basically we're going to have a function of 2 variables, f of x, y, 2 variables, and the functions, we're just going to limit ourselves to the functions defined on a closed rectangle we'll call it R for rectangle. And the rectangle consists of x values between A and B. These are the x values. And then we put a cross or a times symbol here, and then our y values range from C to D. All right. So what we're talking about here, here's a little diagram. Right here we have our coordinate system, x, y, z. This is our rectangle. It's on the xy plane. Our x values go from A to B, and our y values go from C to D. So they form a rectangle in the xy plane. And then floating somewhere over that is our function of 2 variables, f of x, y, and that's in our on our z-axis. All right? So that's the kind of thing we're talking about integrating. Now, this is the process that's involved is similar to when you first were introduced to integrals in Calc 1, where remember you divide up an interval into little smaller intervals, and then you pick a point on each of the smaller intervals. You get a value of your function. You add them all up together and take the limit. Well, this is a similar thing. What we do here is we divide our rectangle R into subrectangles. And after I'm finished writing this stuff out here, I'll show you a diagram of what is happening here. Into subrectangles of equal length. Okay. Delta x, the change in x, is going to be the difference of the 2 x, b minus a, the whole difference of the x values, divided by some whole number m, and and then delta y is going to be some difference in our y values divided by some other whole number n. Okay. All right. Now, so each rectangle or each subrectangle has area equal to the product of the size of its, the length of its side, so that would be delta x times delta y. And we're going to call this area by the notation delta A. Okay. And again, I'll show a diagram in just a minute. And then in each of these sub-rectangles, we choose what's called a sample point. Choose a sample point in each sub-rectangle. All right. Okay. So here is the type of thing that we're doing here. Okay. This is our XY plane. We're not showing the Z plane here, the Z axis here. And here our X is going from A to B. Our Y is going from C to D. So what we do is we're dividing up the X values equally into delta X lengths, and we're dividing our Y, from C to D, for the Y values, we're dividing that up into delta Y lengths. So what we get are what are called sub-rectangles inside the bigger rectangle. And in each one of these rectangles, we choose a sample XY point. So anywhere within those rectangles, we have an XY value. Okay. Then what we're going to do then with these sample points is we're then going to apply those to our function. We then apply each sample point, let's just call it x sub I, y sub j, to our function f of xy, right? And so we get this, we get f at xi, yj, and we multiply it by the delta area. So what this is basically approximates, and I got another diagram for this, this approximates the volume formed by our function f of xy over the subrectangle. Okay. Going here then. Okay, here's our A to B, C to D for Y. We've got all of our rectangles. Here's a particular sample point in the rectangle. So we get its F value, so we get a value up here in the Z, on the Z axis, and we multiply that value there, that length, or height rather, by the area of the subrectangle. And what we get then is the area, because we have height times the area, we get the area of this kind of elongated, cube of some kind, all right? I'm sure there's a better name for that than what I just said. But you get the point. It's just this big column, block column, that it approximates the area that's underneath the surface, right in that section. Okay. Then what we do after this is now we do this, of course, to each of the subrectangles, and we add it all up together. Okay. So, we add together all these volumes. Add together all these volumes. And what we get then is an approximation of the total area formed by the surface over our big rectangle. We get an approximation of the area, of the total volume formed by our function fxy over the big rectangle R AB cross CD. I do want you to become familiar with this notation right here. Okay, this just represents all the x's and y's. So this is like the set of all x and y's, such that x is between a and, well, let me actually, again. X is between a and b, and y is between c and d. Okay, that's a shorthand way. You're going to see it in homework problems and on tests also. So just be familiar with that. Okay, so let's look at a diagram here, approximation. So basically, there at the bottom of this is our rectangle R, and what we've added together then are all of these individual volumes for each of the rectangles. And what this gives us then, this approximates, if we think of this being the surface that's floating above the XY plane, that the sum of all those containers, so to speak, of all those volumes, gives us an approximation of that total volume that's underneath that surface that's floating above. Okay? All right. So let's see here. So we said here we get an approximation of the total volume. So let V be the total volume. So V approximately equals this sum. So what we're doing here, we have to have a double summation because we're adding along the x values and along the y values. So this is from I equals 1 to m, j equals 1 to n, of, we're multiplying together our function. The function value, this is our sample point, times the delta area. And this V is actually the actual volume. So this summation is an approximation of the actual volume. Okay. Now, the deal that you did in first semester calculus is then you let those little intervals get smaller and smaller and smaller, and you took a limit as the number of intervals went to infinity. And we do the same thing here. So as we let the number of rectangles, or shall I say subrectangles, go to infinity, we get this. We get now that the volume no longer approximates, but equals. So this is no longer an approximation. This, limit, messing this up, limit, as both the m and the n go to infinity, of this double summation, I equals 1 to m, j equals 1 to n, of our function value at the sample point times the delta area. Okay. All right. Now this is all really nice in practice and the problems here, except for something that you're going to do in the very first section of homework. This isn't going to be how you're going to be calculating the volumes, okay, by taking this limit like this. What we're going to see is that the integral will give us the volume, will give us what we need, okay? All right. Now, this is how the text actually defines the what's called a double integral. All right. So this is the definition of the double integral. Now, we now have two integration signs instead of just one. In this case, below that, we put the region over which we are integrating. So this is, in our case here, this is our rectangle, AB cross CD, right? And then we have our function of two variables, fx, y, and then instead of putting delta A, we put D capital A. All right. And this then is equal to that above limit. The limit, as both m and n go to infinity, of a double summation, I equals 1 to n, j equals 1 to m of our function at x, I, y, j times delta a, all right? What you see here is some correspondences that you saw in first semester calculus. The double summations are replaced by the integral sign. So we have a double summation, but now in the limit, we just write the double integral sign. The delta A is replaced by D capital A, right? And then this is equal to the volume under f of xy and above the rectangle R. If our function is strictly a positive function. So for right now, we were just looking at a function being a positive function. Going back to this drawing right here, when we do the limit, we get, of course, tiny little subdivisions here, and this is our function here, f of xy being bigger than or equal to 0, and when we add all this stuff together and do the limit, this whole summation gives us the volume under the surface. Okay, all right. Just like you saw in first semester calculus, let me just compare it to that. First semester, you had, say, a function of a single variable that you assumed was bigger than 0. And basically, we had our x-axis and y-axis here. say we have the graph of the function here. Here we have x equals a, here we have x equals b. Let's draw some straight lines up to match the graph. The area is equal to the integral from a to b of our function, right? So this is just extending it now to where we have a base, a rectangle base, and it's going up to a function. Now instead of getting an area, we're now in 3 dimensions and we get a volume, okay? In first semester, we just got an area. Okay. Any question about this? I know it's going through kind of quickly. If you just compare it to what you learned in first semester, it just extends that. All right, let's actually look at a couple of types of problems that you might have connected with this first section here. All right, so, all right, what we're going to do in this first example is the following. We're going to estimate the volume that lies above R equaling 0 to 2 for x cross 0 to 2 for y. That's our rectangle. And below z equaling 16 minus x squared minus 2y squared. Okay. Let me just show you what we're talking about here. I love it when things suddenly disappear on me. Where'd it go? All right, I'm not crazy. I actually didn't see this little drawing earlier. But I guess maybe I threw it away. Oh well. Okay, let me see if my drawing ability is horrific, but basically what we're talking about here, x, y, and z, basically our rectangle is x goes from 0 to 2, y goes from 0 to 2. So this here is our rectangle in the xy plane. And then our function actually is going to kind of come down as x and y gets bigger. And so we're going to have this is our function here, z equals 16 minus x squared minus 2y squared. And so what we're looking at is we're looking at the volume that's captured underneath that function, but yet over the rectangle, all right? I know I'll find this when I don't want to find it now. All right, so how can we do this? Well, basically, we're just going to divide up our rectangle, in this case, and only into 4 sub-rectangles. I mean, you could go crazy with the arithmetic on this, and in fact, computer systems, when they don't know how to figure out an antiderivative and they're trying to figure out the value of a definite integral, all right, they'll actually divide things up, calculate a sample value, and add all this stuff together. and to give you an approximation, because if you can't figure out an antiderivative, then I'm not sure what else there is to do, all right? So what we're going to do here is we're going to just let m equal 2 and n equals 2. What that means is we're just going to divide the x's into two intervals, and we're going to divide the y's into two intervals. And we're also going to choose, because we need a sample point, we're going to choose the center of each subrectangle as our sample point. So when you have these problems, and you do have just a couple of them in homework, they'll direct you as to what to choose for the sample point. All right, so first of all, let's just look at what we're talking about here as far as m equals 2 and n equals 2. Here's our xy plane here, and we know we're going from x from 0 to 2, so here's 0 to 2, y from 0 to 2. So let's complete the rectangle. And we're just dividing each one up into 2. So here's 1, that's dividing the x up into 2, and here is the one here that's dividing the y up into 2. All right. So this then right here is going to be where x is 1, here is going to be where y is equal to 1. Okay. Then we're going to take as our sample point the center of each of these four subrectangles. So what you have to do is figure out, well, what are the coordinates of the exact center, and then we apply that to our function. So this coordinate right here is 0.5 for the x and 1.5 for the y. This coordinate here is 0.5 for the x and 0.5 for the y. This one here is 1.5 for the x and 0.5 for the y. And then the last one here is 1.5 and 1.5. So those are the coordinates of our sample points. All right. And what's the delta A for each one of these subrectangles? 1, yeah. It's delta x over times delta y. Well, our delta x here is just equal to 1, and our delta y is just equal to 1, so our delta area is equal to 1 for each one of those. Okay, so we just apply that formula here. We're going to say our volume is approximately equal to the summation. Now we're just summing from I equals 1 to 2, j equals 1 to 2. We're applying our function to each of the sample points, and we're multiplying all of that by each one by the delta area. So what this gives us then is, okay, let's see. Remember that our function here was z equals 16 minus x squared minus 2y squared. All right. So I'm going to basically, let's write it like this. So I've got 4 points here. So I'm going to have, let's call it z at 0.5, at 0.5. And of course, that's multiplied by our delta area of 1, plus z of 1.5, comma 0.5, again multiplied by our delta area of 1, plus z, let's go up here, plus z at 0.5, comma y of 1.5, again multiplied by 1, and then finally the fourth point, z applied to 1.5, 1.5, and again delta area of 1. So then we just have to plug this into our calculator or just do the arithmetic, and we get the following. So we get 15.25 for the first one, plugging it into our Z. Second one, we get 13.25. For the third one, we get 11.25. And for the fourth one, we get 9.25. Add all these together, and we get 49. Okay, so whatever the dimensions are, this is the approximation of the volume. Okay. The rule that I just used here, where I chose as my sample point to be the exact center of the rectangle, that's called using the midpoint rule. So the rule that I just used is the midpoint rule. Is the midpoint rule. Use the center of each subrectangle. All right. Okay. Now, I want to actually then choose my sample points one other way. Okay, I chose the midpoint. I want to see what I get if I chose as my sample point the left corner of each rectangle. So, suppose I chose the upper left corner, as my sample point. Now in this case, looking here again, just dividing this thing up, X and Y, 1 and 1, this is M equals N, which is equal to 2. Now I'm choosing the upper left, so that would be right here, right here, right here, and right here, the upper left for each one. So what is this? This is 0, 2, 1, 2, 0, 1, and 1, 1. Okay. All right. So then I'm now going to approximate the volume using those sample points. So my volume approximately equals, okay, it's going to be Z applied to 0, 1. And again, my delta area, of course, is still equal to 1, plus Z applied to 0, 2 times my delta area, plus Z applied to 1, 1 times my delta area, plus Z applied to 1, 2 times the delta area. Now what I get here is quite a bit different volume. I get, when I plug in these XYs into my Z, I get 14 plus 8 plus 13 plus 7, all right? And those add up to 42. So notice with the midpoint rule, I had gotten a volume of 49. With this one, I got a volume of 42. I would hazard to guess that the midpoint rule is probably going to give you a better approximation than choosing a corner off to the upper left or any other corner. Because it's right smack in the middle, it'll give you a better approximation. In fact, I believe the text said that the actual volume of this, when you do it with antiderivatives, is 48. So the first one wasn't too bad of an approximation. We got 49 using the midpoint rule. And of course, you know, you could have of course, do the arduous arithmetic with having even more subdivisions and picking and having more sample points and all of that. But on the problem that you've got, it's just where you just divide it up into two. So I try to keep the grunt work a little bit to the minimum with that. All right. There's just one other thing in this section then, and it just is a couple of basic properties of double integrals, which pretty much fall from how this is being defined. And I think these seem pretty intuitive. Number one is this: if we do the double integral over a rectangle of f of xy plus g of xy dA, well, just like in one variable calculus, we can break it up into two integrals. So this is equal to the double integral over R of f of xy dA plus the double integral over R of g of xy dA. All right. So we can break it up. And the second, let's see, there's three of them altogether. The second one then is this. If we do double integral over R, now c is some constant or some number times our function of xy dA. Well, we know in one variable calculus, we can just bring the constant out in front of the integral, and we can do the same thing here. So it's that same constant times the double integral of fxy dA. Again, just bring the constant out front. And then the last one is, in this section, is this. If we have a function f of xy that's always bigger than g of xy, so its values are always greater, then we have this. Then the double integral of f of xy dA over the rectangle is going to be bigger than or greater than or equal to the double integral of g of xy dA. And that makes intuitive sense also, because we're just adding up bigger, taller boxes, so to speak. All right, so we're going to get a bigger value. Now, what we're going to do in the next section, and I think I'll just get a peek at this next section, if you don't mind, because notice so far this is not a practical way to be figuring out integrals, all right? We don't want to do it this way. We're going to be using antiderivatives just like we did with single variable calculus. So what we do here, and this then gets into using antiderivatives, the next section, 15.2, its title is Iterated Integrals. All right. I'll just get this out of there. Okay, suppose again we have a function of two variables, f, x, y, and it's defined over some rectangle. Defined over a rectangle, R equal, again, x goes from A to B, y goes from C to D. The question is, how do we calculate the integral from C to D of this function dy? Now, the function has two variables in it, both x and y. Here, this is a single integral. We're wanting to get its, we're wanting to calculate this. Y is the variable that varies from C to D. Okay, y varies. X doesn't vary at all. So note, because this has y in it, dy, y varies from C to D. We treat x as if it were a constant. This is very similar to how we did partial derivatives, where we did the partial derivative with respect to y, we treated x like a constant. Except now, we're doing anti-derivatives, all right? So I'll do one example and that'll be it. Very similar to what we did with partial derivatives. Okay, and this is all going to get tied in with what we had talked about. Of course, that won't happen until Wednesday. But let's just do this one example here. Integral from 1 to 2 x squared y dy. All right. So y varies from 1 to 2. X is treated like a constant. Okay, so of course I want to get the antiderivative of this. So can anybody hazard to guess or tell me what the antiderivative would be?
1/2 x squared y squared.
Yes, 1/2 x squared y squared. Exactly. Okay, we just carry the x squared over. It's a constant. We keep it. But then we have to get the antiderivative of y, because that's our variable. And so the antiderivative of y is 1/2 y squared over 2. And of course, the better way to write this is 1/2 x squared y squared. All right? Now, this is a definite integral, so I put my brackets. And this is where y is equal to 1 and y is equal to 2. So I then have to plug in values, but I'm only plugging in y values. So let's plug in the top value, y equals 2. So that's going to be 1/2 x squared times 2 squared. And then minus, and now we plug in the value of y of 1/2 x squared times 1 squared. And let's simplify all this, and we end up getting what? 2x squared minus 1/2 x squared when we simplify and we combine them together, and we get 3/2 x squared. So this is our, shall we say, our answer. This is our evaluation. But notice what we get here has the variable x still in it. That x did not go away. We treat it like a constant as far as antiderivative is concerned. So here, note, what we get is a function of x. All right. Okay. Because when we normally did antiderivatives, we got a number, right? We plugged in, got number on top, minus the number on the bottom, we got a number. This time we've got that x hanging around that we cannot plug into, so what we get is a function of x. And the book uses this as our notation, capital A of x, as our noting the answer. So what we're going to do then next time then is we're going to basically take this. Well, I'll just put a hint of what we're going to do. Okay, this is what we got. We got this. The integral from 1 to 2 of x squared y dy. I'll cut out all the middle part. we got is equal to 3/2 x squared. All right? Now, what we're going to do next then, now, this is for y varying from 1 to 2. Guess what we're going to do next? We're going to have x vary from some number to another number. So, suppose we want to integrate this result from, now x will vary, say x equals 0 to x equals 3, whatever it is. So then we're going to take integral 0 to 3 of 3/2 x squared. This was our capital A of x that we got. Do that with respect to x, and now we will get a number. Now this looks just like plain old first semester antiderivative. We just have x. We're taking the we're taking the antiderivative, and this gives us 3/2 times x to the third over 3 as our antiderivative, and we do it from 0 to 3, and that gives us, what is this, x to the third over 2 from 0 to 3, and when we plug in the top number minus the bottom number, we then get 27 over 2. So what we have done here in this process, we have calculated this. A double integral, the outer one from 0 to 1, the inner one from 1 to 2, x squared y dy dx. This is what we have done. We just did it in 2 parts. This is called an iterated integral. Iterated. You work these from the inside out, not the outside in. Notice the first thing we had done. We did this first, the inside integral first, got our result, and then we did the outside integral. So, big, important thing, work from the inside out. This was our first integral, and then that was our second integral. All right, that's a better place to stop then. I finished, at least finished an example. We'll continue with that then next time.